Laptop also has to be connected to it. That can
Yes, let's see. Let's see. Or else we have to get someone else's laptop, and from that we have to share the screen.
Yeah. I don't know. My laptop internet connectivity some problems. That's what I was saying. Where is it? Oh yeah, it's it.
Can I share screen?
Otherwise, for the session camera. Yes. Oh, camera cable doesn't reach to there.
But board has some problem.
No.
Yeah, I think we can do that. We'll see. But for streaming, we need this, right?
For streaming,
Yeah.
so streaming as well as.
Yeah. So I guess it's somebody else's laptop. Who else laptop is Logan is there. Logan is not on the meeting.
From where I can speak to you? From where I can speak to you? Where do I see?
I'll connect it correctly. Yeah. Okay, well, browser will shoot. Yeah, you can check so what are we streaming then? Only students along with the press basket, these are some. Okay, like good chat. Still anything pending or correct something? We can bring it to the school.
I think Google
בוקר טוב, אבי.
Before I do the meeting, I will talk to you. It's kind of shit. And thanks for being.
I hope everyone has the correction in place, any correction in your names and everything. If anyone please raise your hand.
Yeah, on the second, some board.
Sir, you will. Sir,
I just, one of you can, conflict. Yes. From where?
Vinay, can you hear me?
ಮಾತಾಡೋದ್ರಲ್ಲಿ only mute ಮಾಡಿ so contact
Can you hear me?
ಅದು ಕ್ಲೋಸ್ ಮಾಡಿದ್ದೀರಾ
Mic ಬೇಕಾ
Vinay, can you hear me?
laptop mic. So what? Okay. Yes, that cable. This one. Okay. Yes, it will.
You just tell him to speak one word to just.
What about this thing?
No, no, that they are.
Yeah, like that.
And this one, just.
Huh?
Vinay, you just tell him to speak something, to whether check that audio is correct or not.
Hello, Professor Berman.
No.
Are you able to hear us? I'll leave. Camera, this camera.
He's not talking.
Good morning. Can you hear me?
It's sort of.
Can you hear me?
I cannot, I want to share the screen.
His audio is not connected.
It should come through that speaker. I will check separately. Audio will check separately where it is connected.
No, audio not possible.
Either in the room. See, it is connected.
You can't connect that.
Son. Speakers are laptops. See, this is correct. This is correct. But when he's speaking,
Or else they come here and speak.
mic cannot.
Audio we need to check, right? Vinay, at least this was only we need to do. We need to hear from this guy.
Okay, let's start as early as possible.
Can you speak to him so that we can?
Are we in position?
Yeah, you can speak so that we can check the audio. What he's speaking is not different.
Yeah, but audience, he may like to address audience. No?
He has to speak. Just ask him.
We need to check his sound.
He has to speak so that we hear. Yes, that's done.
Good morning, Avi. Can you hear me?
I can hear you, but I cannot share screen. You ask Vinay to.
Okay, you can try later.
But I can hear you and see you.
Is he permitted to share? Check it once. Yeah, now you can try once again.
Okay.
Probably you are not permitted to share earlier. Yeah, we can see your screen.
Huh?
Can you
Share
still
market.
hear me?
Yeah, can you please, you want to check whether you can share?
Now I can see the slides. Can you see my slides?
No, not now. Earlier once I saw your screen. Yes, I think this is your laptop screen, but it is not a slide. It is a screen with the Zoom title. Yes, I could see something. Now I could see some folders and files. Yeah, now you are seeing. What? Huh? He left this meeting. Okay. Hmm?
Is it possible to call him?
I don't have his number. I don't know whether I can call him on my mobile. Where did I left it? Mail.
His number is central.
Make it mute.
There is his number.
It is from somewhere else.
Yes, yes. It's in,
Where is he?
uh, here. Video is not on, but user. Yes, to unmute him.
Avi, you'll have to unmute and your camera is also not on. Why his screen is not there? It should come on the main screen, no? His screen should come here, no?
Yeah, but he has not turned on his video. Yes.
Done?
But he's still on mute and his video share.
So videos are. Yes, no, but he's not unmuted.
Avi, you will have to unmute.
You see the slide, but not hear you.
We could see your slides. Whether you have permission to unmute.
No, permission is there. He has to unmute himself. No, permission is there, but.
What did you do?
No.
You change the
Full
screen.
But he has not.
Avi, you will have to unmute. And your camera is also off.
Can you hear me now and see me now? Hear me now?
I can hear you,
Okay, so can I start?
but I can't see you. Your
You
camera is
cannot
still.
see me, okay. And now?
Now I can see you.
Okay, I'm sorry for all the trouble. So now you can hear me and see me.
Yes.
Okay, so shall I start?
You can also share. First of all, let me thank you for joining us. We are continuously missing you, but still you are joining us online.
Okay.
You have put off. No, where is he? Whether he has gone out of. Is there? Where is this? I'm not seeing. Only I'm seeing his slide. Yes, he has come.
Okay, thank you very much.
Yeah,
So
thank you.
the talk is about completely positive messages.
First of all, my
Oh.
people will be introducing you. Before that, let me thank you for coming online and inspiring young people. We are around in the audience, so there are about 70 plus. Some people couldn't come because of problem with the flights. Okay, is it all right?
Yeah.
I'll continue. Okay. And right now, Sukantapati, you must be knowing himself and our in-house member, Dr. Vinay, they are taking session since yesterday. And other will be coming very soon, tomorrow, day after tomorrow. Steve will be coming on 15th and joining us. Simo, we are missing him because he messed up with his visa. So he couldn't come. And I'm sorry to say that we are missing him. Anyway, you are available now on online, so I'm very happy. Hope that maybe in the future, I will try to get you physically and enjoy your lectures. And today people are very much waiting for you. Now we already wasted a good amount of time. If you want to say something, please go ahead. After that, one of my team member will be introducing you formally, and then later you can continue with your lecture. Please. You want to ask something?
No, let me start.
If you want to say something, you can. Then later, somebody will introducing you.
Okay.
And I like to tell my audience here, that Avi Burman, he is quite young, still more than 10 years to go to hit century. He always says that he is quite young. So I don't say how old he is. I can only say how young he is. He is very much inspiring. Even now, he is more active than any of us. And I welcome him for delivering this lecture. And please, if you want to say something, you can just tell the people, and then later Divya or Vinay will be coming and introducing. Parikshit will come and introduce you formally. Yeah, please, Avi.
Thank you very much. Okay, the talk is about completely positive matrices, it's an important, interesting class of matrices.
One minute, Avi.
It's a special subclass. Okay. Sorry,
Avi, 1 minute. Here, Parikshit is my colleague. He will introduce you formally to the audience. 1 minute, please.
Okay.
Good morning to everyone. It's my pleasure to introduce Dr. Abraham Burman. Dr. Abraham Burman is an emeritus professor in the Department of Mathematics at Technion Israel Institute of Technology. He earned his BSc and MSc in mathematics from the Technion and completed his PhD in applied mathematics at Northwestern University. Dr. Burman has had a distinguished career at the Technion, serving in academic and leadership roles until retirement in 2011, after which he continues as emeritus professor. His research focuses on matrices, graph theory, and their interconnections, with over 100 publications over influential works on non-negative matrices. He has supervised more than 20 PhD students and co-authored several significant books, most notably non-negative matrices in mathematical sciences. Dr. Burman has also contributed extensively to mathematical education and the promotion of creativity and giftedness in Israel. Over to you, sir. Sir.
Thank you.
Sir, can you please start?
Yeah, please. Okay, thank you very much. So the talk is on completely positive matrices, which is an interesting subclass of positive semi-definite matrices. And it mainly will be a survey, but it has 3 parts. The first part will be a general survey on completely positive matrices. Then we'll talk about completely positive oversets. And in particular, in the third part, we talk about completely positive over the integers. And the talk will use, which is a natural thing in this workshop, we'll use graph theory and later also some number theory. And in the last part, we'll have some new results and also some open problems. So recall that a matrix is positive semi-definite if it is symmetric and its eigenvalues are non-negative. And there are several equivalent conditions. For example, A is positive semi-definite or symmetric and non-negative eigenvalues. This is equivalent to say that A can be decomposed as a matrix B times B transpose. Or all the matrices in this talk will be real, and unless otherwise stated, they'll be symmetric. Another condition is that A is symmetric, and for every vector X, the quadratic form X transpose AX is non-negative. Now, if we consider the second condition, that A can be decomposed as A equals B transpose, and we add another condition that the matrix B is element-wise non-negative, then the matrix A is completely positive. So completely positive matrices, as I said before, is a subclass of positive semi-definite matrices. The name completely positive was coined by Marshall Hall in his book on combinatorial theory. The signless Laplacian is an example of a completely positive matrix because it can be written as a product of the non-oriented incidence matrix times its transpose, and the non-negative incidence matrix has 1 or -1. The non-oriented incidence matrix has rows for the vertices of a graph and columns for the edges. For example, the fifth column, 1, 0, 1, 0, corresponds to the diagonal in the graph. And the product gives us the signless Laplacian, which has the degrees on the diagonal. And unlike the Laplacian that has negative ones, we have ones when I and j are adjacent and 0 if they are not. If we look at the third condition in the definition of positive semi-definite matrices, and the condition was that the quadratic form X transpose AX is always non-negative. But if we want it to be non-negative only for non-negative vectors X, then the matrix is co-positive, and this name was coined by Theodore Motzkin. And these classes of matrices have many applications. For example, block designs, complementarity problems, energy demands, matrix games, exchangeable probability distributions, Markovian models of DNA evolution, max-min efficiency robust tests, Lyapunov functions, modeling optimization under uncertainty, and completely positive or co-positive programming. And let me say a word on this, because this is probably the most important or useful application. Many combinatorial and non-convex quadratic optimization problems that are NP can be written, can be formulated as linear programs, which is, of course, easier to solve. A linear program where the variable are completely positive matrices or co-positive, and there were many surveys on this. Very good surveys are the one by Miriam Duer and Emmanuel Bomze. And a lot of information on these classes are in books that I read with Professor Naomi Shaked-Monderer. The book both books were published in by World Scientific. The book from 2003 dealt mostly with completely positive matrices, and it was extended and dealt mostly with co-positive matrices in the book published last year. And there are two related subclasses. One is a doubly non-negative matrix. We say that a matrix is doubly non-negative if it is positive semi-definite and element-wise non-negative. So obviously, if a matrix is completely positive, that is, if a matrix can be decomposed as B times B transpose, where B is element-wise non-negative, then A itself is non-negative, and by definition, it's positive semi-definite. So every completely positive matrix is doubly non-negative. Similarly, if we look in the other direction on co-positive matrices, a matrix is SPN if it can be written as sum of positive semi-definite matrix and a symmetric element-wise non-negative matrix. And the reason that this is interesting is that positive semi-definite matrices are by definition co-positive, and symmetric non-negative matrices also by definition are co-positive. And the co-positive matrices, and in fact all the sets that we talk about, are convex cones, so they are closed under addition. So if a matrix is a sum of positive semi-definite matrix and non-negative symmetric matrix, then it is copositive. And we look at all these sets, as I said, are closed convex cones, and this diagram describes the relation between them. If we denote by Sn the space of n by n symmetric matrices, then PSDN will be the closed convex cone of n by n positive semi-definite matrices, and so on with all the other classes. So we see in the diagram that the positive semi-definite matrices include the completely positive matrices and is included in the closed convex cone of co-positive matrices. Now recall that if we have an inner product space, inner vector space V, and we have a set K, the dual of K is a set K star of all the vectors that make a non-negative inner product with all the vectors of K. That is, all the vectors that are acute or orthogonal to all the vectors in K. And K star is always a closed convex cone. And here we have interesting relation between the sets that I mentioned, because the positive semi-definite matrices is a self-dual cone. Its dual cone is the same set. Marshall Hall and Maurice Newman in the picture here showed that the dual of the completely positive matrices is a cone of co-positive matrices, and vice versa, the dual of the co-positive matrices is a completely positive matrices. So we have an interesting duality relation between this set, and this is the key for their importance in writing writing combinatorial programs as dual linear programs. Similarly, we have similar relations for DNN and SPN. The dual of DNN is SPN, and the dual of SPN is DNN. As we said, every completely positive matrix is obviously doubly non-negative, and for small matrices, they are the same. Maxfield and Means proved, this is Henrik Means on the picture, proves that for small values of n up to 4, including 4, CPN is the same as DNN. That is, for small matrices, the necessary condition is also sufficient. Similar result by Dyananda was that for small matrices up to 4, the copositive matrices are the same as SPN. But here is an example of a 5 by 5 matrix, that is the matrix H, that is copositive but not SPN. And here is another example of a 5 by 5 matrix that is doubly non-negative but not completely positive. We will show why, a little later, why this is the case. A word about
Yes. Internet is there.
It's only his. He's exited. Yeah, yes, again exited. I think. He has lost connection. I think. Yes. But wait for him. Yes, sir. He possibly lost connection. No, but whether he's aware. No, he's not in the meeting.
Sir, he can.
Can you hear me now?
Yes, yes.
I have to apologize. We are in the middle of a thunderstorm, and these things may happen again. Hopefully not, but we have problems with because of the strong rain. And anyway, let me share screen again. Can you see the slides?
Yeah.
Okay.
But it's not in English.
So there are many applications, but let me jump over it. And
No,
You must have opened different file.
no, Professor Berman, your screen is not shared completely. It is some other window
you
that's
cannot
shared.
see the slides?
Can you share your entire screen? No. Some other window is shared. Could you share the entire screen?
Okay, let me try again. Okay. Can you see the slides now?
Oh, you are in the right file. Right video.
Yes, sir. Now we can see it.
Okay, so I'm sorry for the problems. Let me see if I can continue. Okay. So let me jump over this. I wanted to give here an example of an application of the completely positive matrices to quantum theory, but let me skip it and go to the following question. We want to know, given a matrix, we want to decide if it is completely positive. So we look at the matrix. it must be element-wise non-negative, and it must be symmetric. So this we can see. So given a matrix that is symmetric and non-negative element and non-negative, how can we decide if it is completely positive? So here is a sufficient condition. The comparison matrix M of A of a non-negative matrix A is defined in the following way. We keep the diagonal entries as they are, and we put minus before the off-diagonal entries. And then there is a theorem by Drew, Johnson, and Levy that showed that if A is non-negative and symmetric, and if MFA, if the comparison matrix is positive semi-definite, then A is completely positive. But this sufficient condition is not necessary. If we look at a 3 by 3 matrix of ones, all the entries equal to 1, clearly it is completely positive because it is a column of 1 times the row of 1s. But if we look at the comparison matrix, we see that the comparison matrix has -1 as an eigenvalue, and so it is not positive semi-definite. So we have a sufficient condition, but it is not necessary. This is Drew and Charlie Johnson in the middle and Rafi Levy on the right. As a necessary condition we already mentioned, if A is completely positive, it must be positive semi-definite. So we have the following. Given that A is element-wise and non-negative and symmetric, if M of A is positive semi-definite, then A is completely positive, and A is positive semi-definite. So natural questions are, when is the sufficient condition necessary, and when is the necessary condition sufficient? And now to answer these questions, I want to use some basics from graph theory. The graphs in the talk will be simple, and we recall that the clique number of a graph is the cardinality of its largest clique, the largest set of vertices that all are connected, all connected to each other. The chromatic number of the graph, P of G, is the smallest number of colors needed to color the vertices of the graph in a way that adjacent vertices have different colors. Obviously, the chromatic number is greater than equal to the clique number. Let's look at 3 examples. For a triangle, both the chromatic number and the clique number is 3. For a square, both the chromatic number and the clique number is 2. We need 2 colors, and every edge, and the edges are the largest cliques. For the pentagon, the chromatic number is 3. We need 3 colors, but the clique number is 2. So here we have inequality, strict inequality. Also recall the definition of induced subgraph. If we delete some vertices from the graph and all the edges adjacent to these vertices, what we get is an induced subgraph. For example, if we look at the house graph on the middle, the pentagon is a subgraph, but it's not induced. The square and the triangle are induced subgraphs, because if we delete the upper vertex, and the adjacent edges, we are left with a square. So the square is an induced subgraph. And if we delete the bottom vertices and the corresponding edges, we are left with a triangle. So the triangle is an induced subgraph. And also recall the definition of a perfect graph. A graph G is perfect if the chromatic number and the clique number are the same for every induced subgraph of G. Bipartite graphs are perfect. The house graph is perfect, but the pentagon is not perfect. The perfect graph, the strong perfect graph theorem says that a graph G is perfect if and only if neither G nor its complement contains an induced odd cycle of length greater than 3. It is important that these subgraphs are induced, the cycles are induced. This theorem was proved by Maria Chudnovsky, Robertson, Seymour, and Thomas. The perfect graph theorem, the perfect graph theorem, was proved by Lovash and says that the graph G is perfect if and only if its complement is perfect. Of course, the strong perfect graph theorem implies the perfect graph theorem. The theorem of Maria and his colleagues implies the result of Lovash, and both theorems were conjectured by Claude Berge in 1961. So it took 35 years for the theorem to be proved. Obviously, Maria is in the middle. Claude Berge is on the left, and Don Lovash is on the right. A line graph of a graph G is a graph that is obtained from G in the following way. The vertices of the line graph are the edges of G, and two such vertices are adjacent if and only if there are incident edges in G. For example, if we look at a square with an additional edge, its line graph is the house graph. And we say that the graph is line perfect if its line graph is perfect. So again, a graph is line perfect if its line graph is perfect. And Trotter proved in 1977 that the graph is line graph if and only if it does not contain an odd cycle of length greater than 3. We call such a cycle a long odd cycle. A triangle is a short long cycle, odd cycle, and the pentagon or septagon and all these are long odd cycles. Now, please observe that here the cycles are not necessarily induced. Why is this related to completely positive matrices? I will see in a minute. And for this, we need the definition of what we mean by a graph of a symmetric matrix. So if we have a symmetric matrix A with an n by n symmetric matrix N, its graph has n vertices, 1, 2, up to n, and we have an edge between I and j if and only if Aij is non-zero and I is different from j. We don't consider loops. And we say that A is a matrix realization of its graph. For example, if we remember the 3 by 3 matrix of ones, which was a counterexample, it was the example that showed that the sufficient condition is not necessary, its graph is a triangle. So A, this matrix A is a completely positive matrix realization of the triangle. If we remember the 5 by 5 examples that showed that the necessary condition is not sufficient, its graph is a pentagon. B is a doubly non-negative matrix realization of the pentagon. It's not completely positive, but B plus I, if we add 1 to the identity, it is completely positive matrix realization of the pentagon. Now, if A is completely positive and its graph contains no triangles, then the comparison matrix is positive semi-definite. In other words, if the graph of the matrix has no triangles, is triangles free, then the sufficient condition is also necessary. And with the paper with Nomichak and Monterer, we showed that this, in fact, is a characterization of being triangle free. Now we want to consider the necessary condition and the question when the necessary condition is sufficient. And so we define a graph to be completely positive if every doubly non-negative matrix realization of the graph is completely positive. And Natalie Kogan proved in her thesis that a graph G is completely positive if and only if it does not contain a long odd cycle. And this, as we saw, is the equivalent to saying that the graph is line perfect. I want to briefly go over the main points of this proof. First, we observe that a long odd cycle is not completely positive. And to do it, we consider a k by k. So suppose we have a k by k, a long odd cycle of length k. Consider the matrix B with k rows and k minus 1 columns. Written here, the last row is 1, minus 1, 1, minus 1, so on up to plus or minus 1 according to k, and the last entry is 0. And we consider the product B times B transpose. A is B times B transpose. So A is a product of B times B transpose, so it is a positive semi-definite. And this is how A looks. And if K is odd, then it's also non-negative. So if K is odd, A is doubly non-negative. If K is not only odd, but it's greater than 5, then it does not contain, then its graph is a K cycle, so it does not contain a triangle. And so, as we saw, A is completely positive if M of A is positive semi-definite. But if we compute the determinant of A, we see that independent of K, for every K, the determinant of the comparison matrix is -4. So the comparison matrix is not positive semi-definite, and this shows that A is not completely positive. And this, of course, shows that a K cycle of length, when K is odd and greater than 4, is not completely positive. Then, with in a paper with Danny Erskowitz, we showed that a graph that contains an odd cycle of length greater than 3 is not completely positive. And here we use the fact that the cone of completely positive matrices is closed. And in a paper with Bob Groen, we proved that bipartite are completely positive. So the graphs, not only the graph does not have odd cycles of length greater than 5, it does not have cycles at all, bipartite graph. So bipartite, and we showed that bipartite graphs are completely positive. And in the paper with Natalie Kogan, we showed that graphs Tn, a graph Tn consists of n-2 triangles with a common base. So T1 is just a triangle, T3 is one triangle, and T2 is 2 triangles with a common base. And we proved that the graphs Tn are completely positive. Another definition that you all know is a graph is disconnected. It has K components that are component and pairwise disjoint induced subgraphs of the graph. For example, here we have 3 components. If a graph is connected, it has only one component. A vertex V is a cut vertex if when we delete it, we increase the number of components. A block is a connected subgraph without cut vertices. A block of a graph is a subgraph of G that is a block and is not properly connected in any other block subgraph. In this example, we have 4 blocks, the 4 triangles, the 2 disjoint triangles, and the 2 triangles in the butterfly. I realize that there are too many definitions, but the point is just to show you, give you the flavor of the book. So finally, in the paper with Natalie Kogan, we proved that if V is a cut point of the graph G, G1 union G2, where V is the only cut vertex of the graphs, then if G1 and G2 are completely positive, so is the graph G. And to complete the proof, we show that if G does not contain a long odd cycle, then every block of the G is either bipartite, so it is completely positive, or K4, so it is completely positive, or Tn. In all these cases, all the blocks are completely positive, and the graph is completely positive. So let me summarize this part of the talk. Let A be a symmetric non-negative matrix. Then, if the comparison matrix is positive semi-definite, A is completely positive, and this implies that A is positive semi-definite. The sufficient condition is not necessary, as the example of the 3x3 matrix of ones shows, but it is necessary if the graph of G is triangle-free. The necessary condition is not sufficient, as is shown by a 5x5 matrix, but it is sufficient if the graph of G does not contain a long odd cycle. It is line perfect. Actually, we can take these 2 things to get a characterization of bipartite. For every matrix realization A of a graph G, this condition is equivalent to saying that G is bipartite. So this ends the first part of the talk, and now I want to talk about complete positivity over sets. Are there any questions? If there are no questions, let me continue to the second part. Can you still see and hear me? Can you see and hear me?
Yes.
Can you hear me?
Yes.
Okay, let me continue. Let S be a subset of R, a subset of real numbers. We say that the matrix A is completely positive over S if it can be decomposed as B times B transpose where B is non-negative, and its entries belong to S. And we say that the S CP rank of a matrix A is the smallest number of columns in such B. And we'll consider 4 cases. The case where S is equal to R is what we discussed so far, the completely positive matrices. And in this case, the smallest number of columns of B is called the CPR of the matrix A. If S is the set of rational numbers, we'll talk about complete positivity over the rationals. And in this case, we'll consider 2 parameters, QCPR and RCPR, and in few slides, we'll see why we talk about 2 parameters. when S is the integers, we'll talk about complete positivity over the integers. This will be the third part of the talk, and we'll talk about the number of the columns of B. The smallest number of columns in B will be denoted by I CPR, integer CPR, and we'll also consider the case where S is just the numbers 0 or 1, and we'll talk about the binary CPR. The signless Laplacian that we saw earlier is an example of a completely positive matrix over 0, 1. And we'll consider the following questions. Suppose A is a completely positive matrix, that is, A can be decomposed as B times B transpose, but B is non-negative real number. And we know that where it is given that the entries of A are in S. Does it imply that A is completely positive over S? And in this case, what can be said about the SCP ring? We already talked about R, so what can we say about the CP ring? The CP rank of a matrix is always greater than equal to the rank, because it really tells us we decompose the matrix A as sum of rank 1 matrices. If R is smaller than 3, then the CP rank is the same, is equal to the rank. But here is an example of a 4x4 matrix where the rank is 3, but the CP rank is 4. In a theorem with Francesco Barioli, we showed that for R greater than R, the CPR rank is bounded by R times R plus 1 over 2 minus 1. It is a Theodori kind type of theorem, but and this bound is sharp. What can we say about the CP rank in terms of the rank? If A is completely positive matrix of order n, and if n is less than 5, the CP rank is smaller, less than equal to n. So in other words, we have factorization by square matrix to square matrices. But here is a 5 by 5 matrix. This is a graph of a bipartite graph, and the CP rank is 6, greater than the order. Of course, we can use the result on the rank to get a bound in terms of the order, but this bound is not tight, There was an interesting conjecture by Drew, Johnson, and Levy, and they conjectured that the CP rank is bounded by n squared over 2. It's not true in general, but it holds in many important cases. For examples, when the graph of A is completely positive, or when the graph of A is triangle 3, or when the graph of A or when the comparison matrix is positive semi-definite. What can we ask when the set S is rational numbers? If A is a completely positive matrix whose entries are rationals, does it mean that A is completely positive over the rationals? So A can be factored as B times B transpose, where the entries of B are non-negative real numbers. Can it be factored as B times B transpose, where the entries of B are non-negative rational numbers? Due to Sikerik, Sharban, and Valentin proved the following. They showed that the answer is true if the matrix lies in the interior of the cone of CPN. If A is a rational matrix that lies in the interior of CPN, then it is also completely positive over the rationals. So for this, it is important to know what is the interior of CPN, and Miriam Duer and Steele proved that characterize these matrices. A matrix is in the interior of the cone if it can be written as B times B transpose, where the matrix B consists of a non-singular positive matrix C and a non-negative matrix D. Here we have an open problem. We said that if the matrix B is in the interior of the cone, then the answer to the question is yes. But it is not known what if the answer is positive, if the matrix is on the boundary of the cone. So here is an open problem. Let A be a rational number, a rational matrix that lies on the boundary of CPN. Is it completely positive over the rationals? Why did we need two parameters for the CP rank? Because the following conditions, the following things are equivalent. A is BB transpose where B is non-negative rational matrix, or we can write it as A is X times D times X transpose, where X is non-negative rational matrix, and D is a diagonal non-negative rational matrix. In other words, what we do in both cases, we write the matrix as sum of rank 1 matrices, but in a different way. But these conditions are equivalent. In one direction, we just take D to BI, and in the other direction, we write the DI as a ratio of non-negative integers, PI over QI, and apply Lagrange four-square theorems to PI times QI. Lagrange four-square theorem says that every integer, every non-negative integer can be written as sum of 4 integer squares, of not more than 4 squared. Every non-negative integer can be written as sum of 4 integer squares. So we denote by Q CPR the smallest possible numbers of columns in B, and we denote by R CPR the smallest possible numbers of columns in X. And the Q CPR is of course greater than or equal to R CPR. Here is an example. If we take the 1 by 1 matrix 7, its Q CPR is 4, but the R CPR is 1. R CPR is greater than or equal to CPR. Here is an example of a 4 by 4 matrix. The CPR is 4, and the R CPR is 5. If A is completely positive over the rationals, and the rank of A is R, the same results that we had with Francesco Barioli holds here. The RCPR is bounded by R plus 1 over 2 minus 1. Now a few words about the case where S is equal to 0, 1. We say that the matrix is completely positive over 0, 1 if it can be decomposed as A equals BB transpose, where the entries of B are 0 or 1. And the smallest number of columns in B in such decomposition will be denoted by B CPRA, the binary CPR. Let A be a completely positive matrix whose entries are 0 or 1. Is A completely positive over 0, 1? So the same question, or similar question, but here's the answer is not necessarily true, in most cases not. For example, sorry, we can ask two questions. Let me repeat it. We can ask two questions. Let A be completely positive matrix whose entries are in 0, 1. Is A completely positive over 0, 1? Here the answer is, as we see, very limited in a minute, but we can also ask, let A be an integer completely positive matrix. Is A completely positive over 0, 1? And we'll see the answers to these questions. So first of all, the only way for a 0, 1 matrix to be completely positive over 0, 1 is that it is a direct sum of the matrices full of ones. So not too interesting. Suppose A is an integer completely positive matrices. If n is 2 by 2, for 2 by 2 matrices, A is completely positive over 0, 1, if and only if it is diagonally dominant. And in this case, BCPR A is the sum of the diagonal matrix minus A1, 2. There is similar result for n equals 3, and a similar result for n equals 4. This is a result by Dahl and Hauptmann. And in general, we can say the following: if A is an integer completely positive matrix, such that G of A is triangle 3, then A is completely positive over 0, 1, if and only if it is diagonally dominant. And in this case, the binary CP rank A is 3 over 2, the trace of A, minus 1/2, the sum of the entries of the matrix A. And if A is completely positive over 0, 1, then for all I and J, AII is greater than or equal to AIJ, and the BC and the binary CP rank is greater than or equal to the maximum, to all the diagonal entries. So now we move to the third part of the talk, where the set S is the integers. Any questions? Okay. A matrix A is completely positive over the integers if A can be decomposed as A equals BB transpose, where the entries of B are non-negative integers. The smallest number of columns of B in such decomposition is called the integer CP rank of A, and is denoted by ICPRA. Is every integer completely positive matrix completely positive over the integers? What can be said about the integer CP rank? So the answer in general is no. If n is greater than 2, the answer is no. Consider the matrices, the following matrices. First row 1, 1, 1, and on the diagonal we have 1, A, B, second and 0 in the 2, 3, 3, 2 case. If A and B are greater than 1, then the matrix is integer. It is completely positive because it's positive semi-definite and n is less than 4, but it is not completely positive over the integers. A similar example is the following. First row 2, 3, 1, second row 3, 5, 3, third row 1, 3, C, and if C is greater than 4, the matrix is integer, it is completely positive, but it is not completely positive over the integers. But, we'll see in a minute. For 2, the answer is yes. But first, before, what can we say about a 1-by-1 matrix? So if we have a 1-by-1 matrix, the question is, given an integer matrix, given an integer number, a non-negative integer number, can it be decomposed as sum of integer squares? This is exactly the Lagrange theorem. The Lagrange theorem said that every integer, every non-negative integer is a sum of 4 integer squares. So ICPR of a number is 4, is less than or equal to 4. This is a Lagrange theorem, and it has an important addition added by Legendre. By Lagrange theorem, every natural number is a sum of 4 squares. When can it be written a sum of less than 4 squares, a sum of 3 squares? And the answer is a natural number can be written a sum of 3 squares if and only if it is not of the form 4 to the k times 8a plus 7. So if a number is not the form 4 to the k 8 plus 7, and it is in integer, it can be written as sum of 4 squares, or sum of 3 squares. But if it is in this form, it can only be written as sum of 4 squares. And the simplest example we saw already is 7. The only way that 7 can be written as sum of squares is 4 plus 2, 1 plus 1 plus 1. It is 2 squared plus 1 squared plus 1 squared plus 1 squared. Elena Smigos and Tom Laffey proved that every 2-by-2 integer completely positive matrix is completely positive over the integers. How did we show it? Let A be in the form A, B, B, C, and we want it to be doubly non-negative, completely positive. In case for n equals to 2 is the same as doubly non-negative. So we want A, B, and C be non-negative, and we want AC to be greater than or equal to B squared. They proved that in this case, there is another integer completely positive matrix A prime, B prime, B prime, C prime, that have the same integer CP rank. And in this case, A prime and C prime are greater than or equal to B prime. This is important because now they could show that every 2-by-2 completely positive matrix A is completely positive over the integers, and the number of columns in B is at most 12. Because if A is in the form A, B, B, C, be an integer completely positive matrix, and by the proposition C is greater than, we can assume that C is greater than or equal to A without loss of generality, and by the proposition A can be taken to be greater than or equal to B, then the matrix A can be written as a matrix of B's plus diagonal matrix, where in the diagonal be A minus B and C minus B. And by Lagrange theorem, the integer CP rank of the first matrix is at most 4, and the integer CP rank matrices of the other 2 matrices also at most 4, and obviously the rank of X plus Y is bounded by the rank of A plus the rank of Y, and so the ICP rank of A is less than or equal to 12. But Laffy and Smigos proved also that the number 12 can be reduced to 11. But it cannot be reduced to 8. Because if we look at the matrix A1, 8118, it can be written as B times B transpose, where B has 9 columns, 2, 0, 1, 0, 1, 0, 1, 1, and 0, 1, 0, 1, 0, 1, 0, 2. But it cannot be written, B cannot, the number of columns of B cannot be smaller than 9, because B must have a column 1, 1, because this is, and the only way to write 7, B must have the column 1, 1, because the off-diagonal entry of B is 1, and the only way to write 7 as sum of 4 squared is, as we said before, 4, 1, 1, 1. In a paper of Eliyahu Levi, we managed to reduce 11 to 10. But here we have another open problem. Can the number 10 be reduced to 9? In other words, if A is a 2 by 2 integer matrix, we know that it can be written as B is B times B transpose, where the number of columns where B is non-negative integer matrix, and the number of columns of B is not more than 10. This is a result with Eliyahu Levi that I prove in a minute. I'll discuss in a minute. But the question is, can we have a matrix B with only 9 columns? We know that we cannot have it with 8. The open problem is, can a 10 be reduced to 9? So how do we prove that the number can be not more than 10? We write 3 conjectures. Conjecture 1, every 2 by 2 integer doubly non-negative matrix A can be decomposed as A equals BB transpose, where B is an integer non-negative matrix with 9 columns. Conjecture 2, for every 2 natural numbers A greater than B, there exist integer non-negative vectors U and V with 5 entries, non-negative vectors U and V with 5 entries, such that the inner product U times U transpose is A, the inner product V times U transpose is B, and V transpose is less than equal to B. This conjecture will imply conjecture 1 that we are interested in. Conjecture 3 says that for every 2 natural numbers A and B, there exist integer non-negative vectors U and V with 5 entries, such that V is bounded by U, VU transpose is A, and VU transpose is B. Obviously, conjecture 3 implies conjecture 2, that implies conjecture 1. So all we have to do is prove conjecture 3. So if one proves conjecture 3, it will also prove the open problem. So here is an outline of the proof of Eliyahu Levi and myself. The theorem says that every 2 by 2 integer completely positive matrix A is completely positive over the integers, and the number of columns of B is not more than 10. Without loss of generality, we can assume that C is greater than equal to A. By the proposition of Laffy and Smigos, we can assume that C is greater than equal to A, which is greater than equal to B, and B is non-negative. If B is equal to 0, then ICP rank of then A is diagonal matrix, and by Lagrange theorem, its ICP rank is 8, is less than or equal to 8. So we can assume that the vector, that B is positive, is a natural number. So if B square is, and now, if B square is less than or equal to 3, to C, then we can write A as a rank 1 matrix, 1 B square, plus the diagonal matrix A minus 1 and C minus B square. And the ICP rank of this is less than or equal to 9, because the ICP rank of the first matrix is 1, it's a rank 1 matrix, and by Lagrange, the ICP rank of A minus 1 and C minus B square, each of them is less than or equal to 8. So together, it's less than or equal to 9. This is great, but so now we can assume that B square is greater than C square, than C, greater than or equal to A, greater than B, greater than 0. So let A be such a matrix. If A is less than, and we do the following. If A is less than or equal to 64, we prove conjecture 3. We show conjecture 3 in the following way. If A is B transpose with B constructed using conjecture 3 in the following way, the first row is the entries of U, U1, U2, U3, U4, U5, and the rest entries are zeros. And below the U's, we put the V's, that by conjecture 3, VI is less than or equal to UI, and the remaining entries are W1, W2, W3, W4, which is a decomposition of C minus the sum of VI squared. If A is greater than 64, then C is greater than 64, and then B is greater than 8. And so we can write B, we can write A as A times, we take the entries of A and write them modulo 8. So A is 8T plus alpha, 8R plus beta, 8R plus beta, 8S plus gamma. And we can delete a matrix where all the entries are 8R plus beta, and the remaining matrix will be diagonal 8T minus R plus alpha minus beta, and 8S minus R plus gamma minus beta. And then, and we want to show that this matrix satisfies the condition that, that we need, that we don't need, that ICP-RA is less than or equal to 10. And for this, we need the following definitions. We say that a number X is good if it is 1 or 2 or 3 or 4, 1 or 2 or 3 or 5 or 6 modulo X, modulo 8. So number is good if X modulo 8 is 1 or 2 or 3 or 5 or 6. These are numbers that by Lagrange theorem can be written as sum of not more than 3 squares. A number X is bad if modulo 8 it is 0 or 4 or 7. So it's bad if it is not good. Now we say that a triplet EFG is good if at least 2 of the numbers E minus F, F, G minus F, these are the numbers that we got in the diagonal matrix before. If at least 2 of these numbers are good, we say that the triplet is good. If all 3 numbers are good, we say that the triplet is very good. And if all three numbers are not good, if at least two of the numbers are bad, we say that the triplet is bad. Now, if alpha, beta, gamma is very good, then by Legender's theorem, the ICPR of A is 9, which is great. But if it is good, then by the same theorem, its ICP rank, it should be ICPR A is less than or equal to 10. If it is bad, then we subtract from the matrix A rank 1 matrix xy times xy, where x and y are integers such that x and y and xy are greater than between 1 and 7, are natural numbers, smaller than 7. Since A is less than 64, the resulting matrix is still non-negative. This is why it was important to consider to deal first with the case that A is less than equal to 64. So it should be here A greater than 64. So we denote by alpha prime, alpha minus x prime, alpha minus x squared modulo 8, by beta prime, beta minus xy modulo 8, and by gamma prime, gamma minus y minus gamma minus y squared modulo 8. Then we get A as x squared xy y squared plus a matrix where all the entries are 8r plus beta prime, plus a diagonal matrix where with the diagonals 8t minus r plus alpha prime minus beta prime, and 8s minus r plus gamma prime minus gamma prime. And now we prove, now we prove that for every bad triplet alpha, beta, gamma, we can, there is a pair xy as we need, xy are natural numbers, and also xy and also xy are between 1 and 7, such that alpha prime, beta prime, gamma prime is very good, and this completes the proof. Are there any questions so far? Again, I'm sure that it was too fast and too much information to be able to get all the details, but I tried to show the flavor of the proof. And let me complete the talk with the following observation. If we don't consider if we don't need the matrix to be non-negative, we have a theorem of Mordell that says that a 2x2 integer positive semi-definite matrix, positive semi-definite but not necessarily doubly non-negative, any two such matrices can be decomposed as B times B transpose, where B is an integer matrix with not more than 5 columns. The theorem was proved by Mordell, but there was some gap, and Schinzel, another number theorist in Poland, corrected this gap. And then they showed that 5 can be reduced to 4. We need only 4 columns, if and only if the determinant of A can be expressed as a sum of 3 integer squares. That is, if and only if the determinant of A is not of the form 4 to the k, 8 plus 7. Any questions? Okay, if there are no questions, let me complete the talk with 3 photos. The one on the left is Mordell, The one on the right is Shinzel. And this is a picture of the Baha'i temples in Haifa. You are all invited to visit. And thank you. These two words in Hebrew says, thank you very much. Thank you very much for attending. And I guess now you are ready for lunch, and I am ready to have my breakfast. Thank you very, very much. I hope you were able to see the slides and to follow the lectures. Can you hear me?
Slides were visible, no problem. Can you hear us? Can you hear us?
You could hear me. Okay, great.
Can you hear me?
So let me close the, let me,
Okay.
okay,
Hello?
any question?
Avi, this is Sukanta. Can you hear me?
I hear you, yes.
I was trying to ask this question. That the last thing you were discussing, this is 2 by 2 PhD matrix.
Yes.
And has there been any specific result about, like, if I am considering 2 by 2 for rank 1?
Sorry, I could hear you, but I couldn't understand what you said. But let me explain what I try to do in the talk. First I gave a general talk, a general survey of complete positive matrices, and then I concluded with considering the question for integers. But for integers, the main result was that 2 by 2 matrices can be written as a product of a 2 by 2 integer matrix times its transpose. And the question was how many columns you need.
Right. So for that, so that when you are considering 2 by 2 PhD matrices, instead of that, if I ask the question of 2 by 2 PhDs but rank 1 matrices, is there any answer to that, or like will that be again requiring? Can the answer be 9 there?
Again, I don't think I understood the question, but let us do the following thing. If you can email me the question, I'll email the answer. Okay, let's try to do it in this way.
I have one more question.
Yes, let me try.
So that instead of 2 by 2 matrices, if I ask the same question for 3 by 3 matrices.
Then again, if they're asking, please ask again.
Instead of 2 by 2 matrix, PhD matrix.
Yes.
Okay. If I ask the question for 3 by 3 PhD matrix, 3 by 3 positive semi-definite matrix. So I want to write a 3 by 3 positive semi-definite matrix as product of 2. And how many columns would I require?
Again, I have the same problem. I hear you, but I don't understand what the question. Let's try to do it by email. I'll see I'll read the question and answer immediately.
Okay.
Is this okay?
This is okay.
Okay.
Yeah.
Thank you very much again.
Thank you again, Professor Berman.
Yes.
Yes, I will contact you about the details for the next talk.
Okay.